Okay, you guys, so sorry. I'm getting this all situated. Okay, hopefully we're good to go and you can sort of see my face in the corner and you're seeing lecture 12 Factorial ANOVA and in the full screen. So I'll obviously test this out later and make sure that that is true. So I am just going to walk you guys through the Factorial ANOVA PowerPoint. I actually don't normally do this. For students, I do a lot of just like talking about Factorial ANOVA on the board, and we do a lot of examples. And I just sort of like throw the PowerPoint out there for people who want it, who feel like that would be helpful, but actually don't usually go through it. So I'm going to go through it just because I think that in an online format, it might be really helpful for you to have it. So that's why we're going to do this. So a lot of this, though, you've seen before. So keep that in mind. It's not going to be new to you. Okay, so the very first thing is that we talked about this in class. Factor is also known as an independent variable. In the book, it might even call it a grouping variable, but it's basically when we think of cause and effect or cause and outcome, it's our cause. So in a factorial design, we actually have two or more independent variables. So this makes it different than a one-way ANOVA, okay? Because in the one-way ANOVA, you just have one independent variable. Your independent variable could have lots of conditions or levels. So like you're like, okay, I'm gonna look at what kind of animal pet makes people the happiest. And you're like, I'm gonna look at people who have dogs, cats, turtles, rabbits, fish, whatever, however many animals you want to look at, you can do that. But it's still one independent variable, and that's called pet. Okay, so you have a pet, and it could be one of these different levels or conditions, but that's still one independent variable that we're looking at or we're interested in. In a factorial design, you have to take an independent variable and you're basically crossing it with at least one other independent variable. So if I'm interested in how does the type of pet that you have impact your happiness, right? What else could I also investigate that might sort of go along with that would impact your happiness? Not something random, but maybe something that's sort of connected to your type of animal. In class, we've talked about some possibilities like the number of that kind of animal that you have. So like having one of those things as opposed to say 5 of those things, right? It might matter. I don't know. We also talked about how much money you have, right? So like if you're somebody who's really well off, like owning a horse could make you happy, right? But if you're somebody who's really struggling financially, like owning a horse might be a real burden. Okay, so lots of other variables we could bring in to try to make it a factorial design. Okay, so we're going to go over a lot of different examples here. In this particular example, we have a drug. So you're either getting the placebo version of the drug or the drug version. And then you have food, which is no food versus food. Okay. So in each of these different conditions, right? So let's say we're looking at the people in the top right box. That would be people who are getting the drug and are not given any food. Okay. People in the bottom left box are given the placebo and they're given food. Okay, so that's just sort of just to orient you to what we're looking at. The smallest version of a factorial design that you can have. The reason that's the smallest version is because if you have a factorial design, you only have, or you can, hold on. So if you have a factorial design, you have to have 2 or more independent variables. So in 2 by 2, each of those numbers represents an independent variable. So the first 2 is an independent variable and the second 2 is an independent variable. So that's 2 independent variables. And then they each have 2 levels because the value of those numbers is a 2. So a 2 by 2 is the smallest kind of factorial design that you can have, because you also can't just have one level of an independent variable. Okay. So you couldn't, like, having something like a 2 by 1 is impossible. That's not a thing. Okay. So a 2 by 2 is the smallest type of factorial design you can have. Let's see here. If you're trying to figure out how many total cells you have or how many total conditions you have, you just take those numbers in your, like, for example, in your 2 by 2, and you multiply them. So if I want to know how many total levels I have, total conditions, whatever, I would just do 2 by 2. So 2 times 2 is 4. Okay. So in a 2 by 2 design, you would have 4 total conditions. And I think you guys probably are already good with that. You can have a 3-way factorial design or more. So for example, a 2 by 2 by 2, that's a 3-way factorial design. You have 3 independent variables. But it does become difficult to interpret it. And you'll see this, you might have already seen it, but when you're talking about your interactions, sometimes it's just hard to talk through it. You're like, how do I explain what's happening in these cells right now? And the more factors you add on to that, the more complicated it becomes. So people do generally just stick at a factorial design that has 2 independent variables. You don't really see a lot more than that very frequently. I'm kind of a crazy person who has a hard time narrowing down my steps. So I will have like 3 independent variables, and then I suffer for it later when I'm trying to figure out what it all means, but that's okay. Okay. So some advantages of a factorial design. See, so you can study 2 or more variables at one time. So for example, we talked about this. So if we're doing the animal or pet or whatever. So let's say that I'm interested in what type of pet brings about the most happiness. And I want to know if the number of pets that you have matters. Okay. So I could be interested in those 2 things separately. Like I could just be like, I want to know what kind of pet brings about happiness, and I want to know if having more of a pet brings about more happiness, right? So I can just include both of those independent variables into one study, and that can be efficient, right? Because I'm like, okay, I don't need twice as many participants. I can just get it all done in one study. And that would be like, if I was just interested in the 2 main effects. Like I'm interested in the main effect of the type of pet you have, and I'm interested in the main effect of the number of pets you have. Okay, so those are my only 2 questions, and that's what I'm interested in. But the real beauty of the Factorial ANOVA, the real advantage of having it, is this beautiful thing called the interaction, okay? Most of the time, if you're doing a Factorial ANOVA, you care about the interaction. And what I mean by that is that you think that combining these 2 variables is going to produce something unique, right? So you're like, okay, I think that the type of pet matters, and I think the number of pets matter, and I think that's going to get kind of weird and complicated when I add them together. So, for example, let's see. This is my personal opinion, so obviously you don't have to agree with me. But I would believe that having 1 dog would be great. But having 5 dogs, I personally would not find that enjoyable experience. And so I might say happiness with 1 dog might be at like an 8, but happiness with 5 dogs might drop me down to a 4. Okay. Now, I might feel differently about some other kind of animal. So, for example, let's say we're talking about turtles. I mean, they're kind of cute and they're confined in a space. So, like, I mean, do you really see that much of a change from 1 turtle to 5 turtles? I don't know, but I'm going to imagine no. So, I'm going to say with 1 turtle, I might be happy at a 6, and with 5 turtles, I'll be happy at a 6. Like, I don't care. Like, turtle's a turtle, number of turtles doesn't matter. That right there is an interaction prediction. Okay, so it's like saying that when I'm talking about dogs, the number of dogs matters for happiness. But when I'm talking about turtles, the number of turtles actually doesn't matter for happiness. Does that make sense? So I'm just trying to find a way where I'm combining two independent variables to create a more interesting story. And so the way that it's written here is that in an interaction, the effect of one variable on the dependent variable is different across the levels of the other variable. So what that means is, let me just use the same example. So we'll say like the effect of number of pets on happiness is different across the different levels of types of pet, right? So it's saying that the effect of the number on happiness changes depending on what kind of type of pet I'm talking about, right? So if I'm talking about dogs, the number matters. If I'm talking about turtles, the number might not matter. So that is what it means to have an interaction prediction. Like you're imagining something's going to happen differently across your different levels of your independent variable, and like based on the other independent variables. So it is a little complicated and nuanced, but the more you try to come up with your own designs and kind of practice this out, the easier it's going to be for you to understand. Okay. Okay, so in this particular example, let's see here. We've got testing the effect of volume of commercial. Okay, so that's first independent variable. And gender, second independent variable, on persuasiveness of the message. Interesting. Right. So we're saying we might have different predictions about how commercial volume impacts the persuasiveness of the message for men and women. Okay. So we have, this is a standard 2x2. We have two independent variables and they each have two levels, and a 2x2 creates 4 total conditions. Okay. So just some terminology here. A cell is each grouping combination in a factorial design. So if I go back over here, this is a cell right here. Hello, cell. That's a cell. Okay. A cell mean is the mean of a particular combination of levels of the variable. So I'm going to go back. We're talking about cell mean. Whatever value you found in here would be a cell mean. Okay. Marginal mean is the mean score for all participants at a particular level of one of the grouping variables. So it's hard to see on this previous slide because we haven't created any actual numbers, but our marginal means are going to be our numbers that we'll find out here in the margins, okay? And they're usually average. So like whatever numbers here will be an average of this one and this one, okay? So that'll be important. And we'll see that in the coming slides. A main effect is the effect of one variable averaged across levels of the other variable. And our interaction effect is the effect of one variable that differs across the levels of the other variable. So we'll talk more about those in a minute. Okay. So I have them divided sort of, if we don't know what the independent variables are, we could have like a main effect for the rows and a main effect for the columns. So the main effect for the rows just tests whether there's a difference between the row means averaged across the columns. And the main effect for the columns just tests whether there's a difference between the column means averaged across the rows. And like I said, we're going to see this in practice in a minute. The interaction effect tests whether the row effect varies across columns or whether the column effect varies across rows. In order to detect an interaction, you're looking for a change in the pattern of the means. And I'll be talking to you about this I'll be talking to you about this a lot more in a minute. Okay, so just to sort of show you what this means here, I have it broken down the way it was described in the previous slide, where you see the main effect for rows and the main effect for columns. So our rows, our main effect is a gender effect, right? Because gender down here is our row variable, I guess you would say. And then for columns, that would be the volume effect. and it has it divided as mean for column 1 and mean for column 2. The interaction effect is whether the gender effect varies across different levels of volume or whether the volume effect varies across gender. And I'll walk through that more as we have actual values filled in here. It'll make more sense. Okay. Let's see here. There you go. Okay. So examples of effects in a two-way ANOVA. So this is an example where you would, it says no main effects or interaction effect, and I'm just going to explain that a little bit because it's sort of debatable. It's a little debatable, especially for the gender. We'll talk about that. First thing, let's start with volume just because that's super straightforward. What it's saying is that, remember, our outcome is persuasiveness. So it's like, okay, for the men who heard the commercials at a soft volume, they were persuaded at 2.5. For the men who heard the commercials at a loud volume, they were persuaded at a 2.5. For the women who heard the commercials at a soft volume, they were persuaded at 2.0. And for the women who heard the commercials at a loud volume, they were persuaded at 2.0. And then we went through and created our marginal means. Those are the means that are on the outside of the boxes. So we created those marginal means to look at the main effects. So if you're talking about volume, we basically averaged the 2.5 and the 2.0 to get a 2.25. And that happened in both columns. So if you're just looking to see, like, does volume matter when it comes to the persuasiveness of the message? The answer is no, okay? Because soft or loud, people are persuaded at 2.25. It doesn't matter, okay? I wish this were the truth because it would be really nice for them to stop making the commercials so loud. That'd be really good. But anyway, so here it's saying no, there's really nothing happening with the main effective volume. They're the same. Okay, so the volume of the commercial does not matter. With gender, we do see a difference in the means. So like for the males, it's like 2.5 and 2.5. So the average is a 2.5. For females, it's a 2.0, 2.0. So the average is a 2.0. So then you're ending up combining, like you're comparing a 2.5 and a 2.0. So you're saying that males are convinced or persuaded at a 2.5, whereas females are persuaded at a 2.0. That means it's a little bit more persuasive for males than females. But this example is going off the understanding that usually small differences in means are not meaningful. So this probably would not be significantly different, and we wouldn't have a main effect. For you guys, though, like when you're talking about these things in your papers, on your exams, whatever, your homework, you can still talk about it. Like you can still say males were persuaded at 2.5, which is higher than the 2.0 for females. Like that's obviously true, and that makes sense. There is definitely no interaction effect. And the way we know this is because we're looking at the cell means for the interaction. And we see that there is no change. So let's look at it going across the rows. So for males, going from soft to loud changes it by nothing. Okay. And for females, going from soft to loud changes it by nothing. Those are the same, nothing, nothing. Therefore, there is no possibility that an interaction could be happening here, okay? You will get parallel lines, and you can actually see that down here in the line graph. They are exactly parallel. Therefore, no interaction is possible. You could do the same thing, and thinking, we don't always cover it both ways, but it's the same idea. So if you're looking at columns, so like for soft volume, going from males to females, you go down by 0.5. For the loud volume, going from males to females, you go down by 0.5. Those are the same change, 0.5 change for both. Therefore, parallel lines. Therefore, no interaction is possible. Okay. So let's look at a different example. This is an example where we very clearly have a main effect for gender. And you know that by looking at the marginal means for gender that are out there on the right. So for males, it's a 2.5, and for females, it's a 6.0. So this is saying that if you're just talking about gender and the persuasiveness of the commercials, women or females are persuaded a lot more than males based on these numbers. Okay, so a 6.0 versus a 2.5. We still don't see anything happening with volume because if you look at the marginal means for volume, you have a 4.25 compared against a 4.25. They're the same, nothing, volume doesn't matter. Okay. There's also no interaction. So going from soft to loud for the males changes it by nothing. Going from soft to loud for females, nothing. Those match, therefore, interaction is not possible. Like I said before, you can also look at it via the columns. So in the soft column, going from males to females increases it by 3.5. In the loud column, going from males to females increases it by 3.5. Those match, therefore, no interaction is possible. You can also see the no interaction being possible down here with the line graph because they're parallel lines. So no interaction could possibly be happening there. Kind of boring. Okay, moving on. In this particular situation, same sort of idea, but I'll kind of clarify this. Okay, so we see like an overwhelming main effect for volume here for the columns, a 2.25 versus a 6.25. So we would definitely be able to say that loud commercials are more persuasive than soft commercials. And we're looking at the marginal means for that effect. For gender, I mean, it's not saying this here, but you do, I mean, they're not the same number. The marginal means are 4.5 versus a 4. So you could say males are slightly more persuaded than females, but it would probably not be a significant difference. For your interaction, if you're looking across the rows, going from soft to loud for males is an increase of 4 points. If you're looking at females, going from soft to loud is an increase of 4 points. They match, therefore, no interaction is possible. Again, you can see that if you look at the columns too. So going from 2.5 to 2 and going from 6.5 to 6, both of those go down by 0.5 and they match. So no interaction is possible. And again, you can see that here, looking at your parallel lines, no interaction is possible. Anyway, so sad. Okay, so let's keep going here. Sorry, my little thing keeps messing up. No, no. Ah, go back. Ooh. It hates me. Well, whatever. I'll figure that out. Okay. So interaction effect. This is also probably this is where it's going to get a little tricky. Okay, so I'm just going to say that. Interaction effects in general can be a little tricky. And the hardest part is just talking through them. So the first thing I want to point out is that interaction effects are only talking about the cell means. So the actual numbers inside the boxes. That's all you really need to look at if you're thinking about an interaction. If you're interested in an interaction, that's what you're interested in. What's happening here? So let's say for our males, when they listen to a commercial at a soft volume, they're persuaded at 1.4. But if they listen to the commercial at a loud volume, they're persuaded at 3.3. So we see that it's going up, right? So if you have the option to play a loud commercial for men, then you should probably do that because they'll be more persuaded by it. For females, we actually see the opposite trend where females are more persuaded by soft commercials than they are by loud commercials. So it's almost the exact reversed effect. And it's actually pretty rare that you get this kind of reversal for an interaction. I mean, it's great, It's like the strongest kind of interaction you have. It's just sort of unusual. But you can see it. It's called a crossover interaction, and you can see that very clearly in the line graph on the bottom right. They're crossing. Okay, so that is your typical crossover interaction. So if you were trying to describe that interaction effect, you'd say that males are more persuaded with loud commercials than soft commercials, but women are more persuaded with soft commercials than loud commercials. Not as hard to explain because it's so clearly opposite for both of them, which actually makes it a little easier to talk about. Backing up to just mention the main effect things. Remember, main effects, we're just looking at the marginal mean. So for males versus females, we have 2.35 for both of them. So we would say there's no difference for that main effect. And then for soft versus loud, the main effect, pretty much non-existent. I mean, soft is slightly higher, but it would not be significantly higher. So here's the thing. If you just look at the marginal means, you just focus on the main effects, you actually miss a whole lot of what's going on here. Okay. So if I were just looking at the main effects, I'd just be like, nothing's going on. Nothing happened, really. Okay. And I would really blatantly miss out on all this information that's being held in that interaction effect. So the interaction effect is going to be really, really important. Okay, let's look at another interaction effect that also has some main effects going on with it. Okay, so let's start with the main effect of gender. So if I'm talking about the main effect of gender, I'm looking at the marginal means for males versus females. So that's my 4 versus 6. And that would just tell me that females are more persuaded than males. Okay, because females have a 6 and males have a 4. My main effect for volume, I'd be looking at a 2 versus an 8. So I would conclude that people are more persuaded by loud commercials than soft commercials. So there's that. But then I can also take a look at the interaction that might be happening inside the boxes. And for males, going from a soft to a loud commercial is an increase of 4 points. For females, though, going from a soft to a loud commercial is an increase of 8 points. So, having to explain this interaction, I would probably say that the effect of going from soft to loud commercials, I would say the effect on persuasion of going from soft to loud commercials is stronger for females than it is for males. There's other ways you could say that. Of course, you could say that if you're looking at the other way, like soft, like if you're looking at that column of soft and you're talking about going from males to females, there's no change. It's a 2 and a 2. If you're talking about loud, going from males to females, you'd see a change of 4. So you could say that when the commercials are soft volume, there's no difference in males and females' level of persuasion. But when the commercials are at loud volumes, women are more persuaded than men. It's another way to talk about it. So, options. Okay, so when there is no interaction effect, the main effects are pretty straightforward and can be directly interpreted. So if you don't have an interaction going on, then talk all you want about your main effects because they're telling you important things. But when you do have an interaction effect, the main effects really, it says cannot, but they really just should not be interpreted without considering the interaction. So some people try to. I remember, I don't know, I was reviewing a paper and people were talking all about the main effects, and then talking about the interactions. And I'm like, I mean, yeah, the main effects just aren't really important if you have an interaction going on because the interaction tells you so much more than the main effects do. So just something to think about as you're reading through papers in your future. Patterns of interaction effects. So this is an ordinal interaction, which means that the order of the means doesn't change as a function of the other variables. So let me just back up really quick to show you the ordinal interaction that we just had. Okay, so 2 to 6 and 2 to 10, going from soft to loud shows an increase no matter what. Okay, the change is different. Like, so 2 to 6 is a 4 and 2 to 10 is an 8. So it's different, but they're both going up. Okay, so we would consider that ordinal. And you sort of see that example here. Sometimes these are a little harder to detect and even harder to explain, especially if the change in pattern is very slight. So we saw a change from, like, we saw 2 to 6 and then 2 to 10. So it was like 2 to 6 was a change of 4, 2 to 10 was a change of 8. Well, what if you're in a situation where you've got like a change of 2 and a change of 3? I mean, an interaction's possible there because they're not matching, but it's a lot harder to explain because the shift is so small in the pattern. But okay. A disordinal interaction is the same thing as what I talked about earlier with the crossover interaction. This is when the order of the means changes as a function of the other variables and the slopes are running in the opposite directions. So in our previous example, where we were looking at how like men were more persuaded by loud commercials, but women were more persuaded by soft commercials, that's what would be considered a disordinal interaction, or what we call a crossover interaction. Okay. The structural model for two-way ANOVA. So I showed you something similar to this for one-way ANOVA, where we sort of took the total variance and we divided it into between groups and within groups variance. With a factorial ANOVA, the between groups variance gets more complicated because, you know, before it was like chance and a treatment effect, but now really like our treatment effect is like divided into 3 different things. Okay. So in under between groups variance, the treatment effect is now could be factor A, which is like independent variable 1, whatever, factor B or independent variable 2, and the interaction. You've got 3 different things that are all sort of wrapped up in the treatment. Within group variance is still made up of chance, error stuff. Between group variance also still has chance and error in it, even though that's not fully depicted here. Okay. I threw this slide in, so this was not originally in here, but I threw this slide in just to make sure that we all understood factorial nomenclature and that you could talk through it. So I kind of want you to just quiz yourself really quick. So I'm going to ask you some questions and you're going to make sure you can do it. Okay. So in a 2x2 factorial design, how many independent variables do you have? Okay. In a 2x2 factorial design, how many main effects could you have? Okay. In a 2x2 factorial design, how many total groups or total conditions do you have? Okay. Last question's a little tricky. In a 2x2 design, how many interactions can you have? And I'll explain that one. You're probably not going to know. Okay. So the first answer, how many independent variables? Well, if you remember, each number represents an independent variable here. So the 2 and the 2, they're both independent variables. So you have 2 independent variables. How many main effects do you have? 2. Okay, and the reason you know that is that each independent variable has a main effect. Okay, so your answer to how many independent variables you have is going to always be the same as how many main effects you could have. What was my next one? How many total conditions? So 2x2, 2 times 2 is 4. So 4 total conditions. And then how many interactions are possible? Now, it's possible that you might get really wrapped up here in like how many boxes there are and like how many ways you can combine them and think about them and the cell means and how do they all, whatever. But what I want to highlight here is that we have actually only been talking about one interaction. Okay, we've been doing a 2x2 this whole PowerPoint, when we're talking about the interaction, okay? So with a 2 by 2 factorial design, there is only one interaction, okay? And it is the interaction of the first variable with the second variable. Now, yes, that's complicated. Yes, you can use a lot of words to describe that. Yes, it involves four means, like that's fine, but it's still just one interaction that we're talking about, okay? So these two variables can only interact one time. Okay, so hopefully you understand that. And we're going to move on to the 2 by 2 by 2. Okay, 2 by 2 by 2. How many independent variables do you have? Okay. How many main effects do you have? How many total conditions or groups do you have? And then how many possible interactions could you have? Okay, so starting at the beginning, how many independent variables do you have in a 2 by 2 by 2? That would be 3 because there are 3 numbers. Okay, so remember every independent variable is represented by a number. How many main effects can you have? Also 3. Remember, it's going to be the same as however many independent variables you have. How many total conditions do you have? That would be 8. 2 times 2 is 4, times 2 is 8. How many interactions can you have? This one's a little tricky, but the answer is going to be 3. And that's because your first independent variable can interact with the second independent variable. Your second independent variable can interact with a third independent variable. And your first independent variable can interact with the third independent variable. So that's 3. Okay, let's go to the 2 by 3. In the 2 by 3, how many independent variables are there? How many main effects can you have? How many total conditions do you have? And how many interactions can you have? Okay, so the first one, independent variables, how many independent variables are there? There are 2. You have 2 numbers. Main effects, how many main effects are there? 2. Again, the same as the independent variables. How many total conditions can you have, total groups? Well, 2 times 3 is 6. So 6 total groups or conditions. And how many possible interactions can you have? Well, a 2 by 3. So there's only 2 variables there, and they can interact one time. Okay. Let's see here. Moving on to the last one. I just really made this one up because it's crazy and like no real person in their right mind would do this. But imagine you have a 4 by 6 by 5 by 2. 4 by 6 by 5 by 2. Okay. In a 4 by 6 by 5 by 2, how many independent variables are there? How many main effects do you have? How many total conditions do you have? I feel like I might need a calculator. You go the back way, it's a little easier. Like 2 times 5 times 6 times 4. And then how many total interactions do you have? This would also take a hot minute. Okay. All right, so let's talk through that. So first one, how many independent variables do you have? There are 4 numbers, therefore you have 4 independent variables. That you could also say you have 4 main effects. How many total conditions do you have? So I did like 2 times 5 is 10. 10 times 6 is 60. 60 times 4 is 240. This would be insane. But let's just imagine you had 240 conditions. How many possible interactions could you have? Well, let's see. The 4 and the 6 can interact. The 6 and the 5 can interact. The 5 and the 2 can interact. The 4 and the 5 can interact. The 6 and the 2 can interact. And the 4 and the 2 can interact. So I think it's going to be 6 possible interactions there. Anyway, okay, so hopefully that makes sense. There's also the possibility on the exam, which I'm still figuring out, that we would have a situation where it'd say, okay, let's imagine you have 24 total conditions and 3 independent variables. What is a possible factorial representation of that? So if you have 24 conditions and 3 independent variables, okay? So think of it this way, like you have 24 conditions. If you break that down into 2, like what can you multiply by 2 to get 24? It'd be 12, okay? So 2 times 12 equals 24. So 2 and a 12. But I need 3 independent variables, and that's only like 2. So I could break that 12 down further into like a 3 and a 4. So you could have a 2 by 3 by 4, and that would give you 24 total conditions. So once I have a pad or note, I don't know, like a big board or something, I'll try to do that for you guys, but I don't have that yet. So I'll come back to that later. Anyway, I hope that that was very helpful, just walking through the PowerPoint. Of course, if you have questions, just send me an email and I'll happily answer any questions that you have.